Hey there everyone, I am Devang, and in this video we'll be discussing how Facebook's database architecture evolved over time. So let's look at some statistics. Facebook creates 4 petabytes of data every day, which is a million gigabytes, thanks to more than 65 million businesses using its services and more than 6 million marketeers actively marketing their products on the site. These numbers justify how Facebook uses tons of data on a regular basis. But have we ever wondered how it gets stored and maintained efficiently? So in the next slides, we'll look at how Facebook data architecture evolved into handling billions of data fetch operations globally. In 2004, Mark Zuckerberg founded a company called The Facebook at Harvard University, which operated as an online profile that connected students via university's social networking site. The entire platform was hosted on a single rented machine at that time using a lab stack, which consists of Linux as the operating system, Apache as a remote server with MySQL for the database, and PHP as the scripting language. Of course, there was some amount of HTML and CSS for for website styling. The design was straightforward. When a request would come in, the Apache server would receive it, query the database on the same machine, and then return the content to the user. Soon, this product scaled up to 50 other colleges, but a problem arose. The difference in utilization between colleges, for example, a big university in Penn State had over 50,000 students, whereas a tiny university in Ohio might have nearly 1,000 or so. Because of the present architecture, if a large number of Penn State users flooded the server with requests, the hosting machine would go down, which would affect other schools as well. So Facebook chose to segregate its application machine that handled web traffic from its database machine, which kept and served all of the underlying data separately to tackle this problem. Facebook began to skyrocket in 2006, reaching 12 million users in December of that year. So Facebook made some significant adjustments in its entire database model in order to handle this huge traffic. Facebook switched to a polyglot persistent architecture, since initially it was a monolithic architecture, which uses multiple databases with distinct features and data models to implement various system cases. For instance, services like Messenger, photo sharing, social graph, user posting, and other services are loosely connected microservices that work together. Facebook has been utilizing MySQL as its primary database since it started with several engines. It makes use of a social graph to capture and monitor all apps on the site, including who liked whose posts, mutual friends, and who has eaten at a restaurant you're visiting, and so on. Furthermore, while SQL allows for rather strong database operation, it does have limits when it receives over 100 million page views each day and many 100 million daily active users. In order to tackle the problem of SQL, Memcache, an open source cache framework, is used and configured in order to be dispersed across a large number of machines. This allows cache data to be distributed across the cache fleet. It acts as a cache in front of the database, as you can look at the diagram. It blocks all requests of data target that are in the database. However, there is a typically high trade-off between data consistency and high availability. By the end of 2008, Facebook had surpassed a 100 million user threshold, and by July 2010, it had crossed the 1 trillion page views record with half a billion users. To solve the MySQL's high computational drawbacks, Facebook developed Rocksdb, an inbuilt continuous key value storage for rapid storage. The Facebook engineering team wanted in RockDB to be efficient and speedy. The data, although being compressed, took up far more storage space, which led to purchase of further more hardware, which increased the data storage cost. Myrox contributed to a 50% reduction in space utilization while increasing the write efficiency. For its user-facing database, Facebook eventually migrated from InnoDB to Myrox. The switch was rather painless because only the database engines changed, but the underlying MySQL technologies remained the same. The MySQL instance is threefold smaller than the InnoDB uncompressed instance and 2 to 3 times lesser than the InnoDB compressed instance, which is a huge number. In parallel, after experiencing an exponential growth in the amount of data it was receiving, Facebook built an infrastructure to support such big tons of data. For analytics, distributed storage, and MySQL database backups, Facebook began to adopt Apache Hadoop. Although Apache Hadoop seems to be the greatest open source solution for managing big data, other big data management tools such as Apache Thrift, HBase, and Apache Hive have also been employed. Gorilla, which is Facebook's another in-memory database for time series, that's mostly used for supervision and analysis. With minimum running overhead, it can handle breakdowns ranging from individual nodes to vast areas. The graph above for Gorilla positioning in the analytics infrastructure is shown. It has nearly quadrupled in size 2 times in 18 months without requiring any more operational efforts. Some future plans for Facebook that Facebook wants to work on developing more comprehensive features to support MyRocks. The goal of its MyRocks project has been to make storage savings as efficient as possible. It presently lacks certain notable INODB features like some full text and spatial indexes, and online DDL, automation, foreign keys, deadlock detection, and a native partitioning are just a few other features that are currently not available with it. So this was it from my side. If you want some further information about this blog, I have created a separate link, which I'll be putting it in the description. So you can go ahead and check this out. Till that time, keep exploring and keep coding. Thank you.